Good morning. Welcome to Krishna's class. We take up the next step in the proof of the completeness of health. Before that, let us recall the path we are going to trace. We have already seen that in a non-linear space, every Cauchy sequence with a convergent subsequence is convergent. Now, this is the basic result in any non-linear space. Now, we consider LPE specifically for all values of t from 1 to infinity. Now, they are all non-linear spaces. Now, we show that every Cauchy sequence in a non-linear space, in fact, we have shown this, has a rapidly Cauchy subsequence. Now, this is the important thing. We have already introduced what rapidly Cauchy subsequences are. So, every Cauchy sequence in a non-linear space has a rapidly Cauchy subsequence. That is a very straightforward way of constructing it that we have seen in the proof. Now, the next stage then to show that every rapidly Cauchy sequence in LPE for 1 less than or equal to p less than or equal to infinity is convergent. Okay. Now, this is a statement which is not in general valid in non-linear spaces which are not complete. I mean, obviously, they are not valid. Okay. Because you can always construct a Cauchy sequence which does not converge in that space. That is possible. Okay. Certainly, all Cauchy sequences have rapidly convergent subsequence, and if every rapidly convergent subsequence, then it would mean that the Cauchy sequence itself is convergent, but that is not true. So, in general, in a non-linear space, one cannot assert that all rapidly sequences are convergent. But what we are going to prove now is that LPE is a special class. LPE has the property that every rapidly Cauchy sequence in LPE for 1 less than or equal to p less than or equal to infinity is convergent. And therefore, the next step would give you that LPE is complete. So that I will talk about that later. But this is our focus today, that every rapidly Cauchy sequence in LP is convergent. So let us state the theorem. Let E be a measurable subset of R and let then every rapidly converges with A I'll put it this way. A with respect to the LP now. B pointwise almost everywhere on E to a function in fact we prove both in the stage of proving the for A, B would be a part of it. So let us work on this now. See, we prove this in two parts. First, we consider the case all LPE where P is not equal to Q. So, that's the first part. The proof will be in two stages. Stage 1, we assume 1 infinity. And stage 2 will be so these are the two stages in which we prove this theorem. First we prove it for 1 less than or equal to P less than infinity, and almost a similar proof for infinity. Now let us prove this in stages. So stage 1, that is so we start with a rapidly Cauchy sequence in LP. This is for one any P lying between, but we fix P, then talk about it. Okay, so it can be any one of these cases. Now, what we can do is that you see what is the Suppose Fn belongs to LPE for any of these P that I am going to talk about. What do I have? In general, Fn is an extended real valued function. Okay, but it has a property that on or almost everywhere the function is real valued. Okay, so each Fn is an extended real valued function. Almost everywhere it is real valued. Third property is that integral over E Fn mod Fn to the power P is finite. So one an extended real valued function E. The second property is that each Fn is real value almost everywhere on E. That means possibly on some subset of E whose measure is 0, the function may take value infinity plus or minus infinity. But almost everywhere the function is real value. Real valued almost everywhere. Third property is integral over E finite. This is for and for every n. So we fix an n that lies between this and this is. Okay. So corresponding to each p there will be a particular set. So let set of all such that Fn x is that En complement. Right, En complement is and measure of 0. So we'll designate this. Now you take E naught. Then measure of E naught 0. Further, Fn is real value on E slash E naught, which is the same as E naught complement. And then what matters is that, okay, so let us put this across in the following way. We excise this particular E naught from E. Okay. So by possibly EXCI excising from E a set of measure 0, that is E naught. Define what it is. This is your E naught. We may assume that each Fn take real values without loss of generality. We take this as because in integration it doesn't. This integration doesn't. The third statement is not affected because you see that this can be split into integral over E slash E naught plus integral over E naught. Integral over E naught is anyway 0. Therefore, this becomes integral over E slash E. And so therefore, once you take this E, we have the same result. Okay. So let convergent series of positive waves such that we apply the condition that is rapidly pushing such that norm of this is the condition that it is rapidly pushing. Okay, that is P now, that is integral over E more precisely. See, this is what you have, epsilon k to the power, because you see that this 1 to the power 1 by p is less than or equal to epsilon to the power epsilon k square. Therefore, you take the pth power of that. This is what this we shall make use of. Sort of arguments that you need while working on measure, because we are allowing freedom on sets of measure 0, and that will not affect the integral. Now fix number k, since x belongs to E is a new E that we have defined. And this is if and only if mod fk plus 1 now we apply Chebyshev inequality. Which we shall write here. This is what it is. Non-negative measurable function, a non-measurable, non-negative measurable function on any lambda positive measure of the set So this is the Chebyshev inequality, and this is what we apply here. So by Chebyshev inequality, we have measure of the set which is equal to measure of these are the same sets. And this by Chebyshev inequality, can work it out now. Which is less than or equal to What does this mean? This now since P is greater than or equal to 1, the series P converges. Now by Borel-Cantelli theorem, there exists a subset E naught of B with measure 0 and for each x belonging to E slash E naught, there exists an index kx such that mod fk plus 1 x minus f kx. So let x belong to then what we have is the following. Is less than or equal to sigma j equal to n to n plus k minus 1 of jx, which is less than or equal to sigma j equal to n to infinity epsilon j, and this is a convergent, this is the tail of a convergent sequence for every n greater than or equal to kx, and for all thus the sequence series implies is less than or equal to 1 to the series. Okay, this is what we have. Now the series is finite implies the sequence for each k. Now since R is complete, R is complete, what does it say? All Cauchy sequences converge in R. So we are going to use that. Since R is complete, we then have Fk converging to some F on E slash E. limit exists. Let fkx then integral over E to the power 2. Since Fn pointwise, so we have proved one part of the theorem. Almost everywhere on E, take the limit as k tends to infinity in the above inequality. So let me just call this star to infer that since the series converges, F belongs to LP and so we have at one stroke we have proved both that Fn converges to F pointwise almost everywhere on E as well as Fn converges to F in LPE. Okay. So we have proved both the statements in the theorem that means LP convergence and pointwise convergence. almost invisible. So that completes the proof of the theorem in the case where 1 less than or equal to p less than infinity. Okay. So we shall take up the proof of this theorem for the case p equal to infinity. We shall stop at this stage and we'll continue with it in our next lecture. Okay. So thank you very much.